Hello, welcome to the Berkeley Seminar. You all know Kevin Carlson, but you may not know why does it matter that we have infinite sets. But fortunately, Kevin's going to tell us.
I think the title, thanks Sophie, was Does It Matter? Which is a slightly different question, and I'm going to provide an alternative title, which doesn't quite work as a pun because of how the letter N, the phoneme N is pronounced. Is the sound okay?
Can you write in black?
Yeah. Wait, that's not dead, that's just too light. As an alternative title, you could say A Farewell to N. Rough outline. From kind of more philosophical to a little more mathematical. I can probably get a blacker black as well. So this talk is based on this very remarkable little book, The Foundations of Mathematics and the Theory of Sets by JP Mayberry, which is not the sexiest title. And as far as I know, no one else has ever read this book.
Depends on who you are.
Well, yeah. I mean, at best you figure it's just going to be like a book about Zermelo-Fraenkel set theory and about axiomatic set theory. And it is not whatsoever that. Mayberry seems to have been an interesting guy, very good mathematician and philosopher, one of the most legitimately inspiring mathematical philosophers I've read. A lot of mathematical philosophy that I've seen I find not that engaging, but this is the real stuff, I think.
You make it sound as if he's not alive anymore.
He is no longer alive. I'm afraid I don't really remember his biography very clearly, but he has a Wikipedia. And I think lived till about 20 years ago. And I found this book sometime in undergrad. I was telling Sophie before this talk that I had kind of a strong hobby for foundations and logic and stuff in undergrad. I took a great logic course from Dana's student David McCarty, the late David McCarty, who was a thoroughgoing ideological intuitionist. He really believed that the law of the excluded middle is really wrong and that you're confused if you think it's true. Extremely intellectually heroic stance to take, right, and to hold for a whole career. So I always found him very inspiring. And Mayberry is a little bit less iconoclastic than McCarty was, but the argument that he makes in this book is along a somewhat similar line, that maybe you're actually wrong about some of your most cherished beliefs about the basics of math, and maybe that even matters. So the first thing I want to try to say something about is, does the content of this talk or this book, should we care at all? Most mathematicians certainly don't take foundations seriously or really even believe they're real these days. And I think that this is an outcome of foundations being thought of as a part of mathematical logic. When you think about foundations, you think about like the first order theory, ZFC, and models of it, and cool, fun stuff that Joel David Hamkins posts on Math Overflow, but then like that if you're not actually in logic, doesn't really impinge on your research. But I think there's a little bit more of a pragmatist view on foundations that leads to taking them a little bit more seriously. So that's what I was asking in this first section. What's uniquely special about modern math? Actually, this is a little bit much to put on you, but does anybody want to throw out any quarter-baked potential ideas to like what's cool about modern math? Like why does it?
To like other modern fields, or specific other math, or what?
Yeah, as opposed to say other intellectual fields, including contemporary fields, and maybe also to older math if you know anything about history of math. Either way you want to go. that's a pretty hard question, but at least maybe let me take 30 seconds and let people try to decide what they think about it. We're all, to one extent or another, modern mathematicians here, and presumably think that's a good idea. Just 1 second, Sarah, and then I'm curious. So maybe there's some good reason for that. Maybe that actually does something for us. Yeah.
I was going to suggest that I feel like modern math, as opposed to like older math and many other, and some of the fields, has a tendency to sort of allow. It's a little hard to put into words exactly what I'm talking about, but like generativity of entities almost. I think a good example of what I mean is that like people used to argue a long time ago about whether complex numbers or like imaginary numbers are like a real thing, whereas nowadays we're completely content to just say, okay, you can invent whatever new objects you want.
Yeah, I think that's getting at something that I think is very important about the contrast with historical math. Mayberry's is a pretty good historian. He talks a lot about the ancient Greek attitude towards math and numbers, which was in particular that there was no such thing as a number in our modern sense. And the invention of the concept of number in the 17th century, which you can watch Newton doing, because he says weird things, because who's the guy right before Newton? Who's Newton's teacher? Barrow. Barrow can be quoted saying things about how, like, I'm not going to do the thing that Newton's about to do, which is he's like, a number is an abstracted ratio between quantities. There you go. And so for 200 years or so, a number is this abstract object that it's like some kind of, you like consider like the ratio between the areas of two objects and the ratio between the lengths of the two objects, and if they behave mathematically the same, you're like, there's some thing floating around in the Platonic realm that like is the square root of 2, and then I'm going to like do calculations to it. And that's like the 17th, 18th, early 19th century attitude towards number.
Back to the Greeks' magnitudes.
They had magnitudes, but they did not. But they did not think Euclid. Mayberry argues more, much more eruditely than me. Mayberry argues that Euclid doesn't look at this and say, oh, there's this abstract quantity, the square root of 2, that is the length of this line segment. But that Euclid is talking about the line segment. And he multiplies line segments together and gets rectangles, etc. And that's actually conceptually substantially different. That the Greeks don't have some abstract register of being that is where the numbers live that can be instantiated in various different units. And even more clear, or more importantly for Mayberry's mission than the stuff about continuous quantities, which is, I won't really say anything about real numbers. Is the concept of arithmos. Can I spell that in Greek? Which is translated usually as number from the Greek, but which Mayberry adduces many citations to indicate what the Greeks really meant by arithmos is a finite set. And so when we as category, I'm sorry?
We're decategorifying their concept?
Yes, exactly. When we as category theorists go like, oh, well, like addition of natural numbers is a decategorification of the disjoint union operation, this is maybe not so modern as we think. This is maybe just undoing some of the abstraction process of Newton and his heirs and getting somewhat back to the Greeks. That's part, Mayberry relies on that historical antecedent to try to like make this all a little bit less scary. The idea of saying farewell to n. So this is getting at an answer. This is getting towards the answer that I want to make. Did anyone want to say any other suggested maybe answers to this?
I was going to suggest that modern math, compared to both older math as well as certainly other fields of intellectual inquiry, tends to reach consensus about what people think is true or correct. Not always.
Right.
Not always instantly, but I think to a much greater degree.
Right. I think those are like really exactly branches of the answer I wanted to make, which are that in modern math, we seem much less than almost anybody else in time or space, as it were, to argue about what's real. And we seem much less than almost anybody else in time or space to get permanently stuck disagreeing. And that's pretty cool. I think that's actually at the heart of what's so successful about modern math. There's like something, right? I mean, this might or might not come down to that, like we seem to be able to prove things to each other. I put a bit of a question mark there because you can easily get from here to a reductionist thing that is like, oh, because everything we say to each other can in principle be reduced to a machine checkable proof. That's not really the point I want to make, but the possibility of proof of our claims via norms of proof that nobody fundamentally disputes, even if it's a pragmatic norms, I think is at the heart of why modern math works so well.
Does Blavatsky help with consensus, or does he make it more difficult?
Yeah. So of course there's this homotopy type theory program arising from Vladimir Voevodsky's worry that maybe we don't really actually know whether our statements are true because our statements are getting too complicated and our proofs are getting too hard. I think that is mostly an epicycle on this story, that like we're getting to the edge of what human brains can kind of really handle in some of our pure math, but that this is fundamentally not a problem of the math, but just of trying to prove really hard things. And nobody really has the time to sit and actually try to verify these boring lemmas.
I think you see people talking sometimes about like mistakes they find in published papers, and that like are part of like a whole kind of crack of mistakes through like an entire series of published papers.
Mm-hmm.
And like I'm not saying this means that there's something deeply wrong with math as like a whole, but I do think there is maybe a little more than just an epicycle going on here.
Maybe, yeah. So there's room for argumentation about that, and there's room for worrying that maybe there are substantial chunks of math that have real errors. But it is, I think,
I think I understand and agree with your main point.
right. It's right. This is in the end a qualitative pragmatic claim, but the modern math seems to do this better than about any intellectual field, really than any other intellectual field that I have any familiar with that humanities come up with so far. And so that's at the heart of why it's such an intellectual achievement. So that's about what I want to claim as the answer to one. So what makes this possible, that we like pretty much agree like what kinds of methods of reasoning are okay, like what kinds of principles we're allowed to use to like make up new things. We don't worry really about metaphysics. We don't worry very much about what kinds of proof are valid. You know, you don't run into this stuff. We don't have the kinds of problems that Voevodsky has are not the kinds of problems that Italian algebraic geometers have, where it's like, are you allowed to just like vibe out about the nature of a projective surface and like intuit the truth and then say that's what it is? No, right? Like that's not allowed anymore. So what is allowed? Or what is it that that grounds the success, to whatever extent it is success, of modern math? Well, I think there's not like a super standard terminology for this, because in some sense it's just coterminous with modern math itself. But I think what really characterizes modern math is the structural method. You could kind of call it the axiomatic method, although it's begging the question a little bit. The method where you're like, what's a group? It's like a thing that has an operation on it and it satisfies these equations. And then we all know how you prove things about groups, and we learn how to do the right kinds of proofs pragmatically in junior year of college or something. That really, I think, characterizes 20th century and later pure math as opposed to every other intellectual field in time and space, is that like we define structures and prove things just about those structures without regard to like what is the metaphysical nature of the things making up those structures.
Do you think that Einstein, cosmology, and quantum theory have affected math?
Have affected math? Well, certainly inspired things. But then when you do mathematical quantum field theory, you're trying to do things that don't require talking about the actual real universe that exists. When Einstein's results inspire tons and tons of work in differential geometry, but that work is about arbitrary manifolds, and then some physicist has to say, oh, does this apply to the actual manifold of space-time that we really live in? So there are extremely important questions there about mathematical modeling, how it is that a mathematical structure.
Time come to numbers and lengths and quantities and things like that.
You're saying, like, what's the question of how these are connected? Or?
Well, but I mean, we measure space, yes? We think about forces in space and things like that. And so
Right.
we have to have some concept of how we come to conclusions about quantities.
Sure, yeah. And I mean, the question of mathematical modeling and of how it is that a structure like this that has no ontologically specific nature can connect to the world that we actually live in is a really important one. And actually, I think that the focus on the structural method has tended to exacerbate the drift of mathematics away from physics, because we no longer have to think about like our entities as having anything to do with real objects. And so sometimes we don't, and we do motives and things, and that's part of Voevodsky's concern that maybe this consensus drifts away when you get too far out in the realm of building arbitrary structures. But that's a little bit off the direction I want to aim in. So then the last bit of section 1 I want to point out is, like, how does the structural method actually work? What kinds of structures do we define in math? And I'm about to say something that's a little bit controversial for this room. What are our structures made of?
Types.
Maybe, kind of. But as far as mathematicians are concerned, like, I don't know what I can do with types exactly and how to prove things about them, or what a type is. So it's an interesting point, and maybe in 40 years, the next generation will give a real different talk about what the foundation is. But for now, it still seems to be pretty much true that mathematical structures are made of sets. And this is the sense in which I want to say that, like, there kind of is a foundation for math, and it kind of does matter, is that, like, we all seem to basically agree about most stuff in math, and most stuff in math really is actually reducible, not in the, like, proof theoretic hypothetical sense that's not real, really is actually reducible to, like, we're building structures out of sets. Once we build a structure out of sets, we don't care what the elements of the sets are, we think of them purely structurally, and then we're doing category theory. But to actually, like, get started and start making things, we start with sets. And while very wonderful thinkers such as Bill Laver have put a considerable amount of effort into trying to figure out how to get away without doing that, elementary theory of the category of sets, elementary theory of the category of categories, lots of things, I don't think they're, and then as Sarah mentions, type theory, they're certainly not an alternative that's anywhere near as widely satisfactory so far. So that's kind of the philosophical sense in which set theory it really is pragmatically a foundation for math, which leads me to want to say, like, so we're founding math on this, like, annoying first order theory ZFC, or, like, what do we even mean by that? Brendan?
I'm not sure I even understand. Am I meant to understand this claim at this point as well?
The claim that math is founded on sets?
Yeah.
Yeah, no, I think so. Like, I just mean that, like, if you think of any theorem you've proved, I claim that it's probably about a theorem that is probably about structures that are, in the end, built out of interlocking families of sets, satisfying student conditions.
Sets are the C ABI of math.
Yeah. But yeah, I think basically, yeah. Yeah, because we don't, like, think very hard about the individual sets for the most part, but it's not machine code, right? Like, the exact detail, there are certain things that are more like machine code about set theoretic encodings, but, like, when you say there's issues of size and global logic in terms of axioms about categories, but when you say what is a small category, right? It's a couple of sets with a couple of functions.
Sometimes there are interesting theorems to show that a model doesn't exist. There are no sets.
Yeah, yeah. And so that brings up maybe the likeliest disagreement with this ground is to say, like, no, math isn't founded on sets. Math is founded on, like, first-order logic, maybe, on formal syntax and theories in that syntax. And then eventually you talk about models which happen to be built out of sets.
Yeah, so like Brendan, I'm still trying to understand what the claim
Yeah.
actually is. So on the one hand, you're saying that just looking around, we see that what mathematicians get trained in is like naive set theory, and all their proofs bottom out in that sense, and manipulating sets and their elements. And I agree, that's like that's how people are trained, that's how people are thinking. But it seems like you're wanting to go beyond that observation to say that therefore mathematics is founded on sets, and I don't quite see why that follows. Like why is it not just why can't it just be an accident that everyone is working with?
Well, I don't want to claim that math is necessarily founded on sets, but pragmatically, that it is in fact the case that what works so well about the collective sense-making process of modern math is that it was discovered, and it was a very non-trivial discovery, that actually you can encode all of math, at least all of the math that anybody wanted to do in 1920, and for the most part all the way through the 20th century, into the axiomatic method, where you say the kind of thing I'm talking about is sets with these sorts of operations or relations or axioms, and then
So
that's
your
it.
argument is that move was part of how we got to be
Yes,
able to have
yes,
this.
yeah. That it is even the most important factor in that, because there was not the same consensus even in math in 18th and early 19th century math. There was famously you have to be Euler to get Euler's results.
It's like Cauchy's
Right.
theorem.
Yeah, and you can get really wrong theorems even if you're someone as great as Cauchy. And they were sitting around thinking about abstract entities and like knocking them into each other in their little like Kantian minds and like doing obviously incredible things, but things that were not replicable by mortals. And now this stuff is pretty much Pache Voevodsky, but I think it's qualitatively different. It's pretty much replicable by mortals. Was it, Brendan?
I'm not sure how to reconcile this with the fact that like I actually have no idea what's set theory. Like,
Yes,
and I've never
great.
once tried, in terms of reaching consensus with anyone in this room or anyone in my practice of mathematics, I've never once been like, okay, let's take it to the set theory.
I don't mean, when I say it's grounded on sets, I don't mean it's grounded on a particular axiomatic theory of sets. And there's a good reason for that. I was starting to say, in response to Dana, why is it not grounded on like first order logic or something, like we write syntax and stuff? Syntax itself is grounded in set theory, because what is a first order language? It's a set of symbols and a set of terms and a set of relations between those terms. And you at the very least have got to have a very clear idea of what the natural numbers are before you have any chance of talking about a finite string of symbols.
Well, what do you mean by
I
set?
think you have to distinguish between actual physical syntax and the mathematization, the formalization of syntax.
Yeah, but you can't found math on actual physical syntax, because then if I like run out of my board, then you're in trouble, right? You have to explain like how big is it allowed to be or something, right? Math is definitely not. No, this is a reasonable response.
No, I would claim that systems like Lean or whatever are in fact an actual real foundation of math on actual syntax.
I think not, because.
Sorry, this is a tangent.
But it's a good point. Maybe like actual real physical syntax on a computer is better. Well, even in Lean, there are like proofs that are definitely correct Lean proofs, but that like wouldn't fit in any computer that exists, right? So in what sense is it actual syntax? It has to be actual syntax, but in principle.
It's not a proof.
Well,
You haven't shown me a proof.
yeah, but I know that I can like prove that there would be a proof or something, right? Like I can.
Yes, but if you do that, that is a proof. That thing has its own syntax. and
Maybe,
has what
maybe,
makes your
yeah,
account.
maybe. I think that basically putting it on a computer does not change the complaint that
Well, if you want to talk about this more, we can do it later. But I kind of interrupted.
that there are no constraints on what is true or valid in math that have anything to do with the size of the physical universe, and so that you cannot found math on actual physical syntax. And maybe you don't agree, but yeah, let's parking lot that for later.
What about a theorem like incompleteness that there is no proof?
There is no formal proof. That is a theorem. Gödel's incompleteness theorem is a theorem about certain mathematical objects which model the syntax of certain mathematical objects which we call formal proofs because there's a way to interpret them into actual mathematical proofs. But I'm not, when we do proof in math, we don't do formal proofs, right? Like we convince each other of things in ways that like sort of have a lot of similarity, kind of a little to formal proofs that Gödel's theorem is about. But I'm not saying, again, that math is founded on the axiomatic theory, ZFC, certainly not the first order axiomatic theory. I'm saying it's founded on like what is actually true about sets, which is what I want to get to in a second. That's what I want to get to in section 2. What's a set? Great. Can I maybe go on, Sarah?
Yeah, sorry.
Yeah, thanks. Okay, what's even a set? A set is just some definite objects considered as a collectivity. There's a set of those 3 backjacks. And it's funny because you're sort of like flinching and going like, come on, give me a real, but the central observation here is that there is a real theory of actual things called sets that is the actual epistemological foundation of modern mathematics. And that in certain examples, it's completely unproblematic. Giving really nice, simple, uncontroversial-ish examples of sets is a little bit is made a little bit more challenging by the fact that a lot of the time you think about set theory as a theory of pure sets where everything's built out of the empty set. But there's no reason to do that. That's just a mathematical convenience. You can just talk about sets of things. And there is a group structure on the set of, I think, yes, there's a group structure. Just had to think whether there are groups of every cardinality. There's a group structure on the set of markers of this board, and I can tell you what it is. And the ontological claim about this is like, is that real? Is the collection of markers on the board real? Well, you might question whether the markers are real. In some sense, like objects don't exist or something, everything, like it's really just a buzz in the quantum field or something. But if you believe that those markers are each individually real, I claim that you believe that the set of all the markers is real. The thing that, if you deny this, then whatever, we can't go anywhere together. But Mayberry's claim, and I follow him, is that a collection of objects is at least as real as the objects that comprise it. So if you give me any 2 things you think are real, excuse me, I will give you a pair whose elements are those 2 things, and you will think it's real too. So maybe let's pause on that.
I'm a little confused about where we're going, right?
Yeah.
So like, why does sets being real or not?
So that helps us.
Question about what makes math.
Because that helps us say like, okay, I said I'm not trying to found math on the axiomatic theory of sets because that's very recondite and we don't know what the, like, how could this be true when we don't even know the ZFC axioms? Right, something like that's a complaint.
I'd rather say that what seems to make this work is that we seem to have strong intuitions about, strong pre-theoretical intuitions.
Yeah. The
Sets are real.
yeah. You can mod out the word real if you want. Why do we have pre-mathematical intuitions about sets which all seem to substantially agree with each other? Because when we talk about sets, my point is just that like we're talking fundamentally about things like, oh, those 5 things on the table.
Can I?
Yeah.
So are you asserting that basically the core thing here is that you can assert a collection, the notion of a collection, basically. Like if you have some things, then there's a thing called set.
The set of those things, right?
Is that
that is
the foundational act of
right.
mathematics?
And that it turns out that if you're willing to consider that
Yeah.
process of
Then you get
collecting
together.
things together, which either because it's ontologically satisfactory or you're just willing to suppose you're going to do that or whatever, then it turns out that everyone will pretty much agree about what then follows that you can do. I can collect those 3 things together, and I can collect those 5 things together, I can union those collections and get the 8 things. And that's one of the axioms of set theory, if you wanted to axiomatize. So you don't have to think about it as an axiom in the sense of the axiomatic method, where you just like make up a rule that models of set theory have to follow. It's more like an axiom in the sense of Euclidean geometry, where it's a common notion that like, look, I can put 2 sets together. And from there, I can develop the whole theory of addition.
Are you moving towards like an elementary theory of the category of sets? Are you saying that sort of thing?
Yes and no. Yeah, yes and no, right? So there are many of these axioms in the sense of self-evident truths about sets are things you can interpret in topos. Some of them kind of are not. Like the operations in here are very material, and it really does help to be able to, if you want to actually like build things that might be a candidate for n or something like that, it helps to be able to do like the singleton eyes operation on a specific set and stuff like that. So yes and no. Did you have something here?
I was actually gonna say a couple of things. I was gonna say that. Sorry.
That wasn't for you. That was for me. Sorry. I want to make sure I get to something concrete before we have to leave.
Well, they're sort of connected. I was gonna say that I actually am a little bit skeptical that people have. I think people have some degree of pre-theoretical intuition about sets, but I think it's very easy to overestimate how much they do when you're very sorting sets. I think people very often get confused about things like, can a set have the same element more than once? Is it ordered? What is it even? I think people get confused by infinite sets more than people expect.
Well, the infinity is an important question that I'm going to problematize here.
And this in particular, and this overlaps with the other thing I was going to say. The other thing I was going to say is that I think in terms of sets being real, what I am far more compelled by the reality of neurology than of set theory. I think singletonization takes you sort of into a more abstract realm. Like, I think a singleton set, or like, I think the fact that you distinguish a singleton set from its element in set theory means that you have to give the singleton set, like treating the singleton set as having its own reality that can be then put into another set, as opposed to being just that object, means that you have to introduce this whole layer of abstract entities. And I think you really are introducing...
I think they're not abstract entities because it's just like one particular singleton, but it's true that singletonizing is a little bit scary.
Because, hold on,
but you don't have to do it, and...
You have to distinguish that marker, the singleton set containing singleton set containing that.
I agree that distinction can be fuzzy, but also you can avoid it. You can say that the only things I really believe in are like sets that have more than one element, and then I can say like, oh, when I talk about the empty set, the empty set's weird, like what do I even mean by nothing? You can be like, no, that's just an encoding where I'm really just talking about the set containing whichever your 2 favorite dudes are. And that is, in fact, it's funny, you keep grabbing things that Mayberry likes too. That is how Mayberry starts.
I was going to connect this to the other thing I was saying, because I think this is the kind of thing that people get tripped up on. People get tripped up on distinguishing singletons and things.
Yeah, this is not to say that there's nothing whatsoever subtle about the notion of set. You have to make sure we're clear that we're talking about, when I talk about those chairs, it's the same set of chairs if I move them around. There's no way to have the exact same chair twice in a set. But once you say those few things, people seem to come to a very tight common understanding of how sets work. With a very, I think it's true. I don't think you can find anyone who has made a pretty moderate effort at, say, the modern axiomatic method, fundamentally disagreeing about what kinds of things you can do with sets. And if you can find a counterexample, I'm interested to hear it. The closest thing to a counterexample, which let me just go on, if you would, is exactly about infinity. And that is the big question that I want to try to say something interesting about here. Because if we're like, math is founded on sets, everybody kind of like agrees on how sets work. You can like do unions. You can go like, what's an ordered pair? I really need these ordered pairs all the time because I need multivariate functions. Is an ordered pair like I have a thing and then I place it in physical space to the left of the other thing? Like that's annoying. Math shouldn't like rely on physical arrangements probably, right? Well, Mayberry's got this fun concept of a symbol-generated abstraction, where he basically says, like, people usually hate the set-theoretic formalization of an ordered pair, where you're like, oh, the ordered pair xy is like the set x and singleton y or something, because that's ugly and weird. But the point is that, like, a set corresponds to something pretty objective. An ordered pair, the claim is, doesn't really correspond to anything objective. We just, like, think about them because of the way we tend to write symbols on the page. So when you give a set-theoretic definition of an ordered pair, which is what gets you off the ground and starting to prove things like, oh, the category of sets forms a topos. This is not saying that, like, this is really, really what an ordered pair is. It's saying an ordered pair really isn't anything. Here's an objective thing that has the properties you need from an ordered pair. I was thinking earlier about that, like, this is sort of the example of a universal property. Like, an ordered pair should be anything such that two ordered pairs are equal if and only if their two parts are equal. So it's like an equality level, a like zero categorical universal property. And so anyway, that's a way of doing that. And then you don't have to care about the encoding. It's saying there is something objective enough that corresponds to this abstraction that just comes from that we write things ordered. So you can, that was, the claim is that the only reason we're asking questions about ordered pairs is because of how our language actually is instantiated physically or maybe even mentally, that, like, we tend to think things in sequence, we write things in sequence. And so we find ourselves writing things basically like this a lot, and then we wonder, like, what is that thing I just wrote down? Well, the fact that you have, like, written some utterance on a page or said it out loud doesn't mean that it, like, corresponds to anything ontologically significant. But, like, we want to talk about these things just to be able to talk to each other. So these encodings that look arbitrary, like that one, are in fact arbitrary because they're a choice of a way to produce an objective correlate to something that you just, like, kind of made up from the contingent properties of being a human. And a much more important example of symbol-generated abstraction that he claims, and I mean, there's long arguments for everything I'm saying in the book that hopefully you would find more satisfying if you get curious than what I can mutter in a few minutes.
And this is a universal property in the sense that,
like, whatever encoding you choose, as long as it has that property of equality being determined pairwise, you then can forget about the encoding. Okay. So Mayberry's other very spicy example of a symbol-generated abstraction is a natural number. So a big concern of mathematical philosophy, maybe the fundamental concern of modern mathematical philosophy, is, like, what are the natural numbers, or do we care, or something? I mean, Dedekind wrote this whole book, Was sind und der Zahlen, what are and what should be numbers, that pretty much answered this question finally, but people have been yelling about it, at least since Newton and friends made up the concept. Why did they make up the notion of natural number?
Was that book about the natural numbers, not the reals?
I think he gets there. I'm not sure if Dedekind cuts are in that book, but it at least starts out about the naturals. Why did they make up this notion of natural number? Because they'd gotten the great algorithms for arithmetic relatively recently. At that point, you write down these symbols and you calculate with them all the time. So you're like, what is this thing that this symbol corresponds to? Well, there doesn't really have to be anything. We know exactly what I'm going to say the, like, objective correlate of a natural number is, and it's going to be a set that has that many elements. This is not going to be equals now. Okay, n is not going to be anything. Or this is maybe equals, for instance, so maybe that's fine anyway. So that's a semi-tangent, just a very cool concept that Mayberry has, that you don't actually, that the natural numbers don't have to be anything. And this corresponds to the structural framework where, like, oh yeah, a natural number is any element of a natural number object, something that satisfies induction. But then the nice thing about trying to construct these objective correlates is then, like, you can actually build up natural number objects without positing yourself a topos with a natural number object or with W types or something. Okay, that was a slightly nonlinear piece of chat. I want to now say a little bit about the mathematics that Mayberry actually proposes as a novel response to some of these questions and partial answers and ideas. Anything else before I go on to 3? That's actually the real title of section 3. Because yes, as Sarah raised, while I claim people really end up agreeing very closely about the behavior of finite sets, that's not quite so easy, especially if you look in historical time about infinite sets. And indeed, the modern axiomatic method founded on sets follows directly on from Cantor being like, oh, guess what? There are infinite sets now, guys. And Hilbert describes that as Cantor's paradise, and that's really arguably the structural method is just working in a Cantorian paradigm of set theory.
Before Cantor really doubt infinite sets?
Yeah.
What they were vague about them?
No, so there's a way to be a little bit more precise about what you mean by doubt infinite sets. What I want to say is that you can think of Cantor's innovation as saying that you can reason about something like n as if it were a finite set. Now, of course, there's obvious ways in which that's not true. You can't assume that it's not in bijection with any of its proper subsets, whatever. If you take away the obvious ways and you imagine you're being reasonably clever, you can reason about n as if it were finite in the sense that you can imagine n laid out as a completed infinity in front of you. And then you can be like, well, okay, I can see all the natural numbers because I'm really big now or something. And so, of course, I can consider its power set, and then all its subsets would be laid out there in front of me. And deal as far as whatever you think you can intuitively do with finite sets, you can intuitively just start doing that to infinite sets too. And that's pretty much the idea of 20th century mathematics, and it leads to a bunch of cool places. But it all relies on this just total leap of faith or intuition or assertion or ansatz or whatever that we can think of all of the natural numbers lined up together in a completed infinity and conceptualize them just as well as I conceptualize those 3 chairs right there. And that's completely not obvious. What's the justification for that? Well, you go oh, well, I have a really clear intuition of n. It's, well, n is just, you start with 0, and you add 1, and then you go on forever. That's hence the title of the section. But
That's simple.
But how big is that ellipsis? It's the size of n. This is the most brazenly, viciously circular definition in all of math. It's not a definition, right? It's saying oh, yeah, but why do co-inductive definitions work, right? Why is it that there is a thing that is the least fixed point of that operation? On what basis do you say that? Well, you either say it based on your pure operational intuition that you're I imagine I'm infinite now and I just go on forever. And we all agree that totally, if it turned out that we were counterfactually infinitely big, then we would go on the same distance for whenever we both went on forever. Which oof. Or you're just I'm just going to posit it as an axiom, and we're just going to go from there. And I think that's what people, in fact, do. You just decide to each other, we're going to act as if we all know what the natural numbers are, and we're going to proceed from there and see what happens. So I think that's not at all self-evident, that there's only one thing that ellipsis could mean. It's been extremely productive in 20th century math to act as if there is only one such thing. But I mean, you certainly can't prove it. And it was not historically considered self-evident by any means. So let's spend a few minutes gesturing at a little bit of math around this question.
Well, hold on. You said were people historically suggesting that there might be more than one thing, which is what people are talking about with the natural numbers? Even if they weren't willing to say that there was a completed infinity, I don't think their much historical precedent for this modern idea that there might be completely non-equivalent conceptions.
Yeah, no. The idea that you would be like, we have two like different models of n and they're like not the same as each other, I think presupposes some of the conceptual background of like of Cantorianism, basically. Like I don't think you can think that thought in the 17th century because you specifically like don't have a concrete enough idea of what you're even trying to talk about. But more loosely, you might model early modern and older mathematicians as thinking about these things as being something like a proper class, being something that's like very big and fuzzy and you can't really like do most stuff to it, but it kind of like it's sort of clear-ish what you mean, but much less so than for those three guys. So what Mayberry proposes is, all right, fine, like let's do some math. That's enough philosophy. Let's add as a common notion to our informal theory of sets that every one-to-one endomorphism of any set is actually an isomorphism.
Sorry. Never mind.
Which says, in other words, right, that every set is finite in our usual terminology.
That it confines in my terminology.
So this is kind of interesting because all of this stuff is like
Oh, right. Yeah, okay.
Iconoclastic in a very orthogonal way to most traditional constructivism, intuitionism, and all that stuff. Mayberry specifically thinks it's heinous to try to put like mental constructions into the foundations of mathematics, so he's going in a very different direction. So really, like all of his logic is just like Brouwer thought that a real number was like a sequence of digits that like could in principle be produced by like a free choice sequence by an agent or something. And in general, constructivism is saying like the things that are real are the things I can really construct. What can I really construct? Well, like in principle, if I were really big, then I could write down that kind of. That's very central to a lot of constructivism, intuitionism. Mayberry's not interested in these operationalist, like building things up. Intuitions being central to the foundations. So he's not going to be worried about stuff like the law of excludimental. He's going to build global functions on the universe of all sets using the law of excludimental. That's not at all the problem he's interested in, which I think is kind of cool.
Function.
Sorry?
What is a function?
Well, in this case, so this is a set. So a function is a set of ordered pairs, blah, blah, blah. The theory deals a lot also with global functions, which are like functions from the class of all sets to the class of all sets, and that you can't give a full definition of. You can say like, well, union is one of them, and like if I've got one that's valued in true false, then I can take their conjunction.
That's also a primitive version of just like he has sort of a naive version of sets, he has an idea.
Right. That's basically that's naive. Yeah, and you can develop, you can develop their theory in a kind of Fregean style if you want. And now you can also, if you're feeling a little bit fuzzy and like eek about all this, you can also then like take this axiom and append it to your favorite axiomatic set theory you want, and just study in the Cantorian world models of the resulting theory. And so this is like, you can treat this as completely normal and non-radical if you feel like it, or you can treat this as like, maybe this is the mathematical universe I really live in. That's your call, depending on how much you like it. But he does both. And so the big question in the back quarter of the book is, if I assume that, can I do any math? Because like then the natural numbers don't exist, right? No infinite set exists. So how, like, the first thing we do in math is like learn to add numbers together, and those numbers are natural. And so is that already doomed? Have I blown all that stuff up? So I have just a few minutes, so let me think. Let me try to give a tiny little resume of some cool results that he gets in this axiomatic theory.
This theory just arithmetic.
It's kind of if you treat it formally inside of a Cantorian standard meta theory, then you can basically ish, yeah. And so then if you know stuff about like for an appropriate precise formalization of this, you can make it bi-interpretable with an appropriate formalization of piano arithmetic. So so in particular, if you know something about non-standard models of piano arithmetic, a lot of that knowledge will transfer, and so some weird things can happen. So what can you do here? You can define simply infinite systems, which is intuitively like something that might serve as a natural number system, where like there's a first element and then there's an operation of successor that never stops. There's a real precise definition you can give of this. And they're proper classes in this theory, because infinity is big. But you can define several ones, such as you can define completely specific ones, the von Neumann or the Zermelo encodings of the natural numbers, which are like the von Neumann is saying that n is the set 0 through n minus 1 and 0 is empty. Zermelo is saying that n is the singleton of n minus 1 and 0 is empty. So those are two different encodings of the natural numbers that are very traditional, and you can define those both in here fine. They just might be proper classes. And so then you can't assume that you can recursively define a bijection between them, because you can prove recursion principles for actual finite sets within the theory, but there's no ability to prove recursion principles for functions between proper classes. And in fact, you can't prove, and in some model theory sense, you can prove that you can't prove that those systems are the same length, have an order-preserving bijection between them. So if you formalize this system in Cantorian logic, there are models in which the interpretations of the von Neumann and the Zermelo natural numbers are different lengths.
Sorry, so what you're saying is that you can't write a formula which is provably a class function from the formula defining the von Neumann ordinals to the. Okay.
Yeah, that's essentially right. So the class functions are things that you have to be able to write down in constrained syntax, basically. Like there's no way to define in the language of what he calls Euclidean set theory an order-preserving bijection between those. So you can have natural number systems, which in particular means there are models where they really aren't in order-preserving bijection, and they really are different lengths. So the key outcome is like you can really have simply infinite systems of different lengths if you don't believe that infinite sets fit the same principles of reasoning as finite sets. Did you want to?
I was going to ask what a class is.
Yeah, that was my question. What is a class?
A class is something that you can cut out with a formula in the language. So you can say like.
Which is different from collecting a bunch of stuff.
Yes. Like you can talk about the class of all singletons, and it's all the things that are sets with exactly one element.
And that thing is just some finite sets.
In this case, yeah, you want to picture this as the set of all finite sets that happen to be singletons.
That's not a set anymore.
But it's not. Yeah, it's not a set inside the theory, because this visibly admits some monic endomorphisms that aren't bijections.
And the grounding of what a class is.
Right.
The grounding of what a class is there are some formulas that hopefully you believe are either true or false of everything, such as like that thing is a singleton. And every such this is maybe not a very good example. Let's see, what's an example you might like better? Maybe like that it is not a set. Maybe you like that better. Like, I think that chair is not a set, and I think the set of those three chairs is a set. So there's a class of things that are actually sets, and a class of things that are not actually sets. That's at least the idea that you, and if you hate it, then maybe you hate it. But that's how the idea works.
So maybe another way to phrase this is, how do you say what a set is?
Have you actually looked at like what it looks like to formulate set theory in first order logic?
But isn't the point that we don't need to do that to make sense of this talk? Like,
Yeah.
that
Yeah,
it's like
a set in non-formal terms. A set is something that's a completely definite collection.
I just asked because for me, I think my understanding of what a class is and why it sometimes makes sense to talk about classes became much clearer once I understood set theory in terms of first order logic. For what it's worth.
I get what a class is in that sense, but I have a feeling like Kevin's playing with the definitions of these things. Like he's saying like,
I think
say set, don't think of like a set as defined by Zermelo-Fraenkel set theory or something.
Yeah.
Think set as just a naive collection of stuff, like of concrete objects. And I'm not sure how to view a class.
Yeah. So again, another thing that Mayberry does to try to help with that is he talks about species rather than class, and a species is basically identified with the formula that defines it. So the thing with a set can be like any collection whatsoever. It can be very heterogeneous, and you just pile things together, or don't even pile them together, conceive them as together. A class has to be pretty homogeneous because there has to be a formula you can actually write down that defines it.
What goes wrong if you say, if you try to, like, the way I would try to define the isomorphism between von Neumann and Zermelo naturals is A goes to B if there exists a partial isomorphism from the von Neumanns up to A through the Zermelos up through B. Why does that partial?
Yeah. So it's something like those partial isomorphisms will have to be themselves restrictions of global functions, and you are trying to use a recursion principle for constructing a global function from like partial. But you're trying to use a recursion principle for global functions that cannot be established.
So is it like only like is induction / recursion like limited to?
Yes. You can prove the coolest. The proof of this is like 6 pages. The coolest theorem he proves in here is that inside this theory, so you might think roughly in the internal language of a topos that like definitely doesn't have a natural number object, indeed just the opposite. You can prove that global functions, class functions, can be defined by primitive recursion if the recursion function is already bounded by some other global function. There's a bounding principle that says like as you're trying to build this function by primitive recursion, if you already know like a finite codomain at each step, there's some kind of bounding principle, then you can do primitive recursion. And it's a very cool theorem. It's kind of hard to explain, obviously, in just a few seconds, but it's awesome. And some of the concrete outcomes, which maybe I'll just say out loud, are he defines numerals and number systems in terms of like what's a objective correlate of doing numerals. Well, you can like decompose a set into like 2s and 1s, and that's like a binary numeral for a set, something like that. So you can do that set theoretically. You can talk about numerals whose like shape is indexed by some simply infinite system. So there's like a sequence of elements of the numeral that comes from the like little total orders that are each element of the simply infinite system. And then you can talk about when arithmetic functions are definable in the simply infinite system you started with, or in some extensions that I've just like not really described how you construct. So let me just say a slightly mysterious sentence that's a little bit more concrete than that, and I'll stop. You can't define addition in the simply infinite system of Zermelo natural numbers, but you can in binary numerals over the Zermelo natural numbers. That's not going to really make any sense. This is somehow kind of like trying to do addition in unary, and you can't. But you can do addition in binary because there's some bound in how many digits the sum of two numbers has. And so you can define the addition. So that's really just a hint that there are some results in here, but hopefully at least a vaguely intriguing hint. And the point is to try to get mathematics off the ground again without assuming there are actual completed infinite sets. And there's a pretty substantial demonstration that you kind of could. So at least you're not forced to believe in n just to be allowed to have any math. And I better shut up. Thank you.
Thank you so much, Kevin.
Thank you.